Welcome to AI Paperslop, where we summarize the latest AI and tech papers. I am your host, and today's paper is called HumanEgo, Zero-Shot Robot Learning from Minutes of Human Egocentric Videos by Leah Wang and researchers at the University of Maryland.
Hey everyone, glad to be here to break this one down.
So, we are jumping right in because the core insight here is wild. The authors basically mathematically prove that you can train robust bimanual robot manipulation policies using just 30 minutes of human egocentric video.
Right, just 30 minutes.
Exactly. Zero robot data required and no internet-scale pre-training. They solve the notorious human-to-robot embodiment gap using arm in-painting and this really novel interaction-centric token representation combined with a flow matching policy.
Which is super elegant.
Yeah, and it gets a 92.5% success rate across real-world tasks, transferring zero-shot to completely different robot arms like Franca and UR10. But the craziest part, the thing that should make every ML engineer listening pause, is that human data actually beats perfectly matched robot teleoperation data in efficiency.
It really forces a total reevaluation of, the whole data collection paradigm in robotics right now.
It does, because as an AI researcher, the holy grail right now is scalable data. The whole field is building these massive server farms, these elaborate teleop rigs, basically assuming brute force scale is the only way forward.
Oh, for sure. Millions of dollars are being poured into these robot data factories.
Right. But this paper suggests we might be bottlenecked simply because we are relying on the wrong data source.
Yeah, we are staring at empirical evidence that a human just, making coffee in their kitchen while wearing smart glasses gives you a fundamentally mathematically superior training signal compared to hours of robot teleoperation.
But of course, to unlock that human video, they had to solve a couple of massive problems, right? The paper talks about the representation challenge and the learning challenge.
Exactly. You have to bridge both the visual gap and the kinematic gap between a human and a robot. And you have to do it with, a tiny data budget.
So let's unpack this visual gap first, because usually this is a nightmare. Trying to train a robot policy on raw human video is, it's kind of like trying to train an autonomous driving model on footage of a guy riding a bicycle.
That is a great analogy, actually.
Thanks. The visual textures, the mechanics, they are totally misaligned. And older visual retargeting methods just shatter if the viewpoint shifts even a little bit.
Right. And point tracking totally misses the global context of the scene. So this brings us to their visual pre-processing pipeline, which is surprisingly lightweight.
Yeah, break that down for us, because they don't do massive domain adaptation, do they?
No, they don't. Instead of trying to make a human hand look like a robot gripper, which is incredibly compute heavy, they just erase the human from the video completely.
Which literally.
Literally. They run SAM2 to segment out the human hand and arm in every single egocentric frame.
Okay.
And then they use Lemma in painting to just, hallucinate the background where the arm was. So the human demonstrator just vanishes.
Okay, wait, I have to push back on that. Because if you delete the human arm from the video, aren't you just throwing away the actual task?
How do you mean?
Like the micro adjustments of the fingers, the angle of approach, that is what defines a grasp. How does a neural net learn to manipulate anything if you've deleted the manipulator from the training data?
Oh, right. Yeah, that raises an important question. And that is where the rendering step comes in. They don't just leave a blank in-painted frame.
What do they put there?
So after erasing the human, they take the tracked 3D object key points and they render a virtual parallel jaw robot gripper right back into that clean scene.
Oh, wow.
Yeah, so the visual encoder only ever sees a purely embodiment agnostic RGB observation.
So no human skin, no complex fingers.
Exactly. No visual noise confusing the network. It just sees this virtual robot gripper interacting with the objects against a static background.
So they completely bypass the whole pixel-to-pixel domain translation nightmare.
Right, which totally solves the visual domain shift. But as you mentioned, that's only half the battle. You still have the kinematic gap to deal with.
Right, translating human motion to robot motion. Because a human hand has, 21 highly articulated joints?
Yep, 21.
And a standard robot gripper just has a 6 degree of freedom end effector pose, plus the open-close grasp mechanism.
Yeah, an SE3 pose in 3D space. Yeah. Mathematically translating 21 dynamic joints into a rigid robotic claw is, it's pretty treacherous.
So how do they get those 21 joints in the first place?
The human demonstrator wears Meta's Area Gen 1 glasses. They have really high quality SLAM and stereo tracking, which extracts the 3D hand key points in this globally consistent world frame.
Okay, but how do you map those down to the 5 key point virtual gripper? Intuition says you would just draw a line from the wrist straight out to the fingertips, right? Like just map the robot's forward axis to that.
You'd think so, but that intuition completely breaks down the second the human performs a pinch grasp. Because when you pinch something, your thumb and index fingertips physically converge to almost the exact same coordinate.
Oh, I see.
Right, so if your primary mathematical axis is built on those 2 points, the axis just collapses. You hit a total mathematical degeneracy.
So the network would just see undefined noise every time someone picks something up.
Exactly. To fix that, the authors went further down the hand. They used what's called a Gram-Schmidt orthogonal frame.
Okay, engineering alert, what is that?
Basically, they build it on the metacarpophalangeal joints, which are just the knuckles at the base of your fingers.
Oh, right, because those don't move together.
Precisely. A Gram-Schmidt process takes those stable knuckle points and forces them into a rigid, right-angled 3D coordinate grid. Since the base of your fingers never collapses into a single point, even during a tight pinch, the coordinate frame stays perfectly stable.
That is super clever.
Yeah, and from that rigid grid, they extract a clean 3D pose and a normalized grasp scalar that basically any robot can execute.
Okay, so we've mapped 21 joints down to 5 stable points. But here is where it gets really interesting for me. Raw 3D coordinates are usually a nightmare for a transformer to reason about on their own. How do they actually format this data?
This is probably the biggest breakthrough in the paper. They introduce interaction-centric tokens, or ICT.
Right, the tokens.
Yeah. Every single entity in the scene, so both hands and all the objects, is encoded as its own 29-dimensional token.
Okay.
And this token contains the entity's type, its pose in a shared reference frame, and crucially, it encodes its relative pose to both the left and right hands at the same time.
I see why that's novel, but I want to challenge that architecture choice. Why use tokens at all? Because in modern 3D vision, we usually just throw dense 3D point clouds at the problem, like Ego 0 does.
Yeah.
Or we use absolute global coordinates. What makes a 29D token better than just giving the model the raw, dense point cloud of the whole scene?
Well, what's fascinating here is the representation ablation study they ran. It answers that definitively. When they tried to learn these tasks using just visual RGB, success flatlined at a dismal 32.5%.
Wow, that's terrible.
Right. Monocular RGB is great for appearance, but it natively sucks at encoding 3D spatial relationships. But the second they injected the ICT sequence, the success rate jumped to 95%.
Wait, a 62-point jump just from changing the spatial data format?
Yep. And the reason it beats dense point clouds is because it's inherently interaction-centric. Point clouds are unstructured, right? You're forcing the transformer to burn tons of compute just figuring out what geometric features even matter.
Right, has to guess what to pay attention to.
Exactly. But by anchoring a token to a specific entity and explicitly handing the network the 6th degree of freedom relative distances to the hands, the token is literally mathematically describing the physics of a grasp.
It's handing it the spatial relationships on a silver platter.
Exactly. It doesn't care about the camera angle or the background at all.
Which brings up that really cool reference frame study in the paper. Because they tested 2 different ways to calculate those relative distances, right? The anchor frame versus the camera frame.
Yes. And the results there are super practical for ML teams dealing with low data. Using the anchor frame, which means calculating distances relative to the manipulated object itself, drastically accelerates learning when you have almost no data.
Like how little data?
Like 4 minutes of training data.
4 minutes? That's insane.
Yeah. At 4 minutes, the anchor frame totally dominates the camera frame. By tying the spatial reasoning to the target object, it gives the network a massive grasping prior. It doesn't waste time learning the basic geometry of contact.
But wait, didn't the camera frame win out eventually?
It did, yeah. Once you scale up to 40 minutes of data, the camera frame overtakes it.
Why does the performance flip like that? If the anchor frame is such a strong prior, shouldn't it keep winning?
The problem with the anchor frame is that it relies on upstream object detection like grounding Dino and SAM2.
Ah, so compounding errors.
Exactly. Any tiny jitter in the bounding box gets baked into every single transformed coordinate in your token. The camera frame is grounded in the raw sensor, so it doesn't suffer from that upstream noise, which means it scales cleaner.
But the anchor frame is totally invariant to camera placement, right?
Yes. So if you're an engineer looking to deploy on a new robot where the camera might be mounted at a weird angle, the anchor frame is absolutely the way to go.
Okay, so we have this amazing viewpoint invariant representation. But we still have to talk about the learning challenge, because deep learning normally needs massive batch sizes and thousands of trajectories. How do you train a reliable policy on 30 minutes of data?
Right, so they use conditional flow matching. It's parameterized by a 6-layer, 8-head transformer decoder.
Flow matching is getting super popular lately.
It really is. It's replacing standard diffusion models for a lot of tasks because it learns a direct velocity field instead of those heavy iterative denoising steps. It maps a straight path from Gaussian noise right into the ground truth by manual action chunk.
Which means super fast inference.
Exactly. Fast inference and really expressive multimodal action generation. But you're right, flow matching alone doesn't fix data sparsity. So they introduce 3 dense auxiliary objectives.
Okay, let's hear them.
Object motion, 2D trace, and latent consistency.
It sounds kind of like a multitask, self-supervised learning setup. Instead of just grading the model on the final action, you're forcing the shared encoder to prove it actually understands the physics of the scene.
That's exactly what it is.
But do these auxiliary losses actually move the needle, or are they just, academic window dressing?
Oh, they definitely move the needle. In the ablation study, when they constrained the data budget to just 15 minutes, the base model only hit a 50% success rate, basically a coin flip.
Right.
But adding object motion, which predicts future 6-TOF trajectories, added 17.5 percentage points.
Wow.
2D trace, predicting visual projections, added another 5 points. And latent consistency added 12.5 points. Combined, they pushed the model to 75% success on half the normal data budget.
That's incredible. The shared encoder is essentially forced to learn a lightweight world model of hand-object interaction.
Precisely. It can't just memorize pixels. It has to learn the physics.
Okay, so the architecture is totally sound, but the ultimate test for us ML engineers is physical real-world deployment. How does it actually perform?
It performs brilliantly. HumanEgo hits a 92.5% average success rate across 4 different physical tasks. Serve bread, downstack cups, water flowers, and adjust table.
I really want to talk about water flowers, because that's not just a pick-and-place task.
No, it's brutal. It's a strict bimanual coordination task. One robot arm holds a spray nozzle over a flower pot, and it has to hold it perfectly still while the other arm reaches over and turns a faucet.
Right. If the timing is off by even a fraction of a second, you pour water all over the table.
Exactly. And HumanEgo scored 95% on this task. That is more than double the best human video baseline.
Which is just insane. But the bombshell finding here, the thing that I think will break a lot of brains, is the data efficiency comparison against robot teleoperation.
Oh yeah, this is the big one.
Because they benchmarked against the ACT baseline, which was trained on 30 minutes of actual robot teleoperation data. And HumanEgo, trained on just 8 minutes of human data, beat it.
It's wild, right?
Wait, I really have to push back here because I'm looking at the co-training ablation study. They ran a test where they mixed 75% human data with 25% robot data.
Yeah.
And the 100% human data got a 95% success rate. But the mix, the 75-25 split, dropped to 90%. Why on earth would adding perfectly aligned ground truth robot data to the training mix actually make the policy worse?
I know, it sounds totally counterintuitive, but you have to look at the data quality metrics in the paper. Human egocentric data just has a way higher signal-to-noise ratio.
In what way?
The kinematics. Human motion is an order of magnitude smoother. The mechanical jerk is way lower than a teleoperated robot arm. Plus, there's basically 0 idle time in human demos.
Oh, right. Humans don't pause mid-task to figure out which joystick axis does what?
Exactly. And just by virtue of having bodies, human demonstrations naturally cover a much broader spatial diversity.
So all these big tech labs spending millions on teleoperation rigs, they're essentially just recording lower resolution, jittery, degraded versions of the task.
Pretty much. The gradient steps from human data are just higher quality. Human video isn't just a cheap substitute. Mechanically and mathematically, it is a superior data source. Putting robot teleoperation into the data set basically acts as a pollutant.
That is going to cause some arguments in the robotics community for sure.
Oh, definitely.
Okay, so if it learns this well, how fragile is it to changes in the physical setup? Because when you deploy, the real world never matches the lab perfectly.
It's incredibly resilient. They got genuine zero-shot cross-condition generalization. It handles novel lighting, random distractors on the table, new objects, all while maintaining an 85 to 91% success rate.
That's solid.
But the craziest part is the cross-embodiment transfer. They took the policy trained on human data and transferred it zero-shot with literally no fine-tuning to totally novel arms, Trossin, UR10, Franca. They even swapped the cameras from RealSense to ZED.
And it just worked.
It just worked. But, to be fair, there is a critical limitation, and it's in the perception front end.
Right, because ML engineers, we tend to treat perception as a solved problem. We just grab whatever tracker is popular on Hugging Face and plug it in. How sensitive is this framework to the hand tracker?
It is the single biggest bottleneck in the entire system. Their hand tracking method study is totally eye-opening. Stereo depth is completely decisive.
Okay, break the numbers down for us.
So the Meta Area MPS stereo tracker, which uses multiple cameras and IMU data, hit the 95% success rate. But when they swapped to a monocular RGB tracker, it was a bloodbath.
How bad?
RealOR hit 45%. Hammer, which everyone uses right now, hit 32.5%. And MediaPipe completely failed. 0% success.
Wait, really? A 0% success rate for MediaPipe? Why does monocular RGB fail so hard when the 2D key point's like perfectly fine on my monitor?
Because monocular networks rely on manopriors to guess depth.
Manopriors.
Yeah, it's essentially a statistical 3D template of a generic hand. Since it doesn't have actual depth data, it uses the template to guess. But guessing depth from 2D pixels is inherently scale ambiguous. It creates systematic depth offsets, sometimes like 5 to 11 centimeters off in the real world.
Oh, wow. So visually it looks fine, but mathematically the hand is hovering in midair.
Exactly. When you pipe those coordinates into an explicit 3D representation like the ICT tokens, it completely warps the relationship between the hand and the object. The policy gets so confused because the labels say the hand is grabbing the object, but the math says it's 10 centimeters away.
So for a 3D policy, temporal smoothness and tracking persistence matter way more than static per frame visual accuracy.
100%. Just look at RealOR versus Hammer. Both had almost identical shape errors, about 1.4 centimeters of deviation. But RealOR beat Hammer by over 10 points simply because its per-frame temporal jitter was way lower.
So the takeaway there is do not cheap out on your perception front end.
Exactly. Stereo depth and temporal smoothness are non-negotiable.
Awesome. Well, to summarize the core takeaways from this paper for everyone listening, by utilizing this interaction-centric token representation and multitask auxiliary dynamics forecasting, HumanEgo basically proves that minutes of lightweight human egocentric video can outtrain hours of cumbersome robot teleoperation for complex bimanual tasks.
It's a beautifully engineered pipeline. It isolates the abstract geometry of the task from the hardware, which unlocks real zero-shot transfer across completely different robotic platforms.
Which leaves us with a really massive industry implication to ponder. If human egocentric data is mathematically richer and vastly more diverse than robot data, and if these models learn better by abstracting away the physical embodiment, are we nearing a tipping point?
A tipping point for what?
For these massive robot data collection factories, are they about to become obsolete? What if the ultimate foundation model for robotics isn't trained by fleets of expensive robots clumsily navigating artificial warehouses, but entirely by everyday humans, just folding laundry and making coffee in their own kitchens, simply wearing a pair of smart glasses? Think about it. Thanks for joining us on AI Paper Slap, and we will see you next time.